get started. Welcome, everyone, for the first talk after the lunch. Let me first start by introducing our speaker for this talk, Laura. Laura is a senior machine learning scientist at Widen, specializing in the authentication domain. She holds a PhD in affective computing from LMU Munich and a background in cognitive neuroscience. So she's definitely not a stranger to complex problems. In her talk today, Teaching Machine Learning Models, Regret, Avoidance, Laura will be sharing with us her insights on how to help ML model avoid bad decision using regret-sensitive loss function. So join me to welcome Laura on stage.
Thank you for the nice introduction. So my name is Laura, and today I'm going to talk about teaching machine learning models regret avoidance with the goal to optimize complex machine learning systems. I didn't know there would be already a nice introduction, so I'm going to reintroduce myself quickly. Yes, I'm working as a machine learning scientist at Widen currently, background in cognitive science, finished my PhD in affective computing, and since then I've been working in fintech. So let's start. As machine learning scientists or data scientists, we're usually focused on the development of a single model or module, some sort of entity. But very likely, if you zoom out of the scope that you're currently working in, this model or module is very likely part of a bigger system. So a system that entails other components, and very likely these components are also not fully independent of each other, but they interact in a complex way. So when we operate in such a complex system with different components, we usually want to make sure, first of all, that the model that we're developing is performing locally. What I mean with that is, at the time point where I call my model, giving the information, data that was available to the model takes the best decision at that time point. But then again, if we zoom out of that scope of that single model, so we look at the whole system, we also want to make sure that this model also makes globally optimal decision within this bigger system of other decision components. So why do we want to focus on the global level? Because with a singular focus on local performance, there might be some performance loss. So there might be some performance that falls through the cracks, and we might not even be aware of that. The general idea that I want to talk about today is, within these complex systems, can we create models that are less regretful about their decisions, given the decisions of the other modules? So now I used the word regret. Here, you also read it in the title, so I think it's good to start with a short definition of what regret is, how it is defined in decision theory. So we usually talk about regret in situations that involve making decisions under uncertainty. That usually means some information about the best path of actions becomes available after I already took the decision. And in such a situation where I make a decision under uncertainty, I can sometimes observe that the action that I took actually turned out to be not the best action. As humans, we have a very natural response to this. This is the human emotion of regret. So if you are currently in machine learning, you might already be familiar with the concept of regret, because it is associated with many different algorithms that involve decision-making under uncertainty. Just to name a few, they're also overlapping a bit. Reinforcement learning, an example of that would be bandit algorithms or online learning in general, but also game theory, or game theoretical applications. So all of them share the same idea that I always compare, for example, a received reward against the optimal reward, the best maximum reward that I could have gotten. In game theory, the payoff that I received in a game compared to the optimal payoff that I could have received given the strategies of other players in the game. So now I use the word complex machine learning system or complex system a few times. Let's start with the definition of how I would define a complex machine learning system. So I'm talking about a software product that involves several decision components. The first one are probabilistic decisions. Of course, I'm a machine learning scientist. I'm talking about systems that involve either statistical models, machine learning models, classical machine learning models, or deep learning models. But then on top, in these systems, we also have human decisions very often. So that means some sort of human feedback input, a human label of any sorts, within the system. And lastly, deterministic decisions. So we're still talking about a software product, so very likely there are also some hard-coded decision rules, business logic, legal and compliance rules that are included in the system. So let's start with a simplified example of a complex machine learning system. So we have a system that entails different machine learning models, in this case 3. We have some human decisions in that system, and we also have some hard-coded decision rules. And let's assume these decision components are, for example, microservices in a microservice architecture, and they also communicate in a certain way. Let's assume via Kafka. For me as a machine learning scientist, how the system, the infrastructure is implemented in detail is often not as important. It's more important to know all the different flows. So how can a data point be propagated through the system? OK, now we have the idea of a complex system. I will add a use case to this, a very simplified use case that I will use as an example throughout the rest of the talk. So let's assume we have a new startup, and we provide a service. And this service is meant to help landlords and bigger housing companies to find new renters for their objects as fast as possible. And we created this complex system that entails several machine learning models, in this case 2. We have some communication, decision from the landlord. We also have some decision rules, deterministic decision rules. And the goal of the system now is to optimize an objective, in our case, the contract completion rate. So we want to get as many potential renters approved by the landlord. But we also don't want to introduce unnecessary costs. So let's look at the potential flow in the system. Let's assume we get an application of a potential renter. And after we receive that application, we're calling our first machine learning model 1. That is renter info ranker that is supposed to determine what type of information should I send the landlord that will let him get him to approve the renter. Let's assume we can send 3 types of information: a bank statement, a proof of income, or some sort of identification. After we called the model, we now send that information to the landlord, and the landlord can now either approve or reject the potential renter. In case of a rejection, he might also send us some additional information about his decision. Let's assume the landlord rejected the renter, and now we use that additional information to call a deterministic decision rule that now says, should we stop that process for the renter here, or should we go into another stage to try to get him approved? Let's assume we say it's worth pursuing, and then we call our last machine learning model. That's also a ranking model that now determines should we maybe provide an additional background check, an employment verification, or a rental history. So these information sources are all a bit more costly, so we only want to apply them or provide them if they're actually necessary. And lastly, after this decision, we'll send the application back to the landlord, and he can finally approve or refuse the renter. So now we have this example use case, and this complex system that I just described comes with some characteristics. So the first one is sequentiality. So these components are called in a sequential order. And then, as a consequence of that, we also introduce some uncertainty in that system. And lastly, these 2 machine learning models that I just described, the ranker models, they're actually contributing to the same objective, right? So we both want to contribute to the contract completion rate. Let's talk about sequentiality. So reasons for sequential decision-making in such a system could be various. One of them could be infrastructure restriction, or infrastructure that has just grown in a certain way. But then we could also have dependency on earlier stages. In our case, for example, We want to call machine learning model 1 first and determine an information source before we make the landlord make a decision. And then on top, we could also have cost optimizations or cost reasons for making sequential decisions. For example, maybe I don't want to call a more costly optimization if it's not really necessary. So in our use case as well, I don't want to call machine learning model 2 and apply these more costly information sources if that optimization is not likely to be successful. And then as a consequence of these sequential decisions that I'm making, there's some uncertainty. What does that mean? That means when I call machine learning model 1 at that point in time, we don't have any information how the other decision components in this complex process will behave. So that means when machine learning model 1 makes its decision, it's possible that this decision turns out to be suboptimal, so not the best decision. And lastly, I think I said this before, in our case here, we also have a shared objective. So the machine learning models in the system are actually contributing to the same higher goal, in this case, the contract completion rate. So now we have a small use case, very simplified use case, and we describe the characteristics of the system. And now it's quite apparent that this system actually has some similarity with the game. When we talk about game theoretical taxonomy, we could actually say this is an imperfect information game or a cooperative imperfect information game. So what do we have at hand? What makes this similar to a game? So first of all, we have a number of different players or decision components. And these players make their moves in sequential order. And they have incomplete information. That means they don't know what the move of the next player will be. In game theory, we call this endogenous uncertainty. And of course, in this specific case, these players also don't play against each other. So we could say this is a cooperative imperfect information game. OK, now we established that our problem or system has some similarity with the game. What we can do now is use a formalization that is very often used in game theory. It's a game tree. A game tree is nothing but a usual normal decision tree where we have the different players, in this case, or decision makers on the different levels of the tree. And then we also have a game state attached to each node of the decision tree. In this case, this is the contract completion status at each decision point. And as you can see here, this tree is quite small. So we have 24 end nodes. But you can imagine quite easily that in a real-world application, in an actual complex machine learning system, this tree would look much bigger. To give you some idea how fast this tree is growing, let's assume for these two machine learning models that we have, instead of 3 options, we would have 6 options, 6 information sources that we can provide to the landlord. And we would already end up with a decision tree with 84 end nodes. Let's assume we're adding an additional machine learning model on top. So another sequential decision, also with 6 options. And we would already end up with over 600 end nodes. So specifically in decision trees where we increase the tree depth, the tree complexity grows approximately exponential. So we're seeing, especially with adding new components, this tree grows quite fast. Extreme example, let's assume we're saying, oh, we can provide these information sources to the landlord singular, but we could also provide them in combination. So let's assume we're allowing for all combinations of these 6 information sources, and this tree would already be with over 60,000 end nodes. So that's just showing how complex these trees can get. But now that we have identified and formalized our complex system as a game tree, we can now look at machine learning model 1. So machine learning model 1 is the first model that we call in the system, and this model is optimized locally. That means the model is supposed to pick the best information source that is most likely to get the renter approved directly by the landlord. When we now look further down this decision tree, though, we can see that some of these decisions might end up more frequently in this type of the branch. So this type of the branch where we can actually repropose the renter to the landlord and still might get an approval. Or some of these decisions might end up more frequently in this dead node here, where we're saying, OK, now we lost all the possibilities to get the renter approved. So we could now identify this as a regret node, a condition where we would say this decision would be regretted by machine learning model 1. Of course, this is a very simple form of regret that we can introduce. There are, of course, more complex regret conditions. In this case, we could also say, for example, whenever the renter is not approved, and we're going in this part of the branch where we're actually trying to repropose the renter. Let's assume the machine learning model 2 is proposing to do a renter history validation, and then the renter is still not approved. You could also say we regret this, because now we applied a costly information source with no results. This type of regret would probably contribute more strongly to cost optimization. In our case, I said the goal was to optimize the system for the contract completion rate. So we'll just assume that these are our regret nodes for now. OK, now we have our complex system as a tree. We identified some regret conditions. How can we introduce that regret into a machine learning model 1? And when we look at it from a game theoretical perspective, there are actually a lot of interesting methods that are specifically developed to optimize a game tree. One of them is, for example, counterfactual regret minimization. But in our case, we don't want to replace the model that we have with something totally new. We just want to integrate the regret information into an existing model. And a simple solution to do that is cost-sensitive machine learning. So the idea here is that we just introduce the regret information during training of a model by increasing the loss for actions that fell into a regret node. So for actions where we would say this one we would have regretted. OK, let's talk about loss functions. How would such a loss function look like? On the left side, you see a typical loss matrix where we have two parameters, the prediction and the ground truth. So for example, machine learning model 1 predicts that banking statement should work for that renter and predicts that this renter will be approved with a banking statement. Then we have the ground truth, was the renter actually approved or not? For introducing regret, we need something a little bit more complex. So nothing that looks like this typical loss matrix. We need to introduce some more information into the loss matrix. So on the right side, you see something I would call a context-specific or also asymmetric loss function, loss matrix. So in this case, we have our ground truth and we have our prediction, but we also have some additional information about the regret nodes. So let's assume every time the prediction of our model was wrong, we want to introduce a loss of 1. But whenever the prediction was wrong, and then we ended up in this dead end in the regret condition, so we actually lost the opportunity to save the renter in an additional step, we want to increase that loss, because we want to say this is the worst type of error that the model can make, and this should be avoided. Maybe short note on that. Even though we can provide or implement custom loss functions with most packages in Python, they usually expect something like that on the left side. So we usually can have a form with two parameters, and we cannot really pass additional information into the loss function. But there is a nice way, a nice workaround we can actually do this, and this is with sample weights. So for everyone who does not know what sample weights are, it's just an array or a list of numbers that determine how much weight we want to give each sample in our data set when we calculate the overall loss. So if we increase the sample weight, we increase the loss for that instance in case it is incorrectly classified. So let's have a look how we can do this in XGBoost, for example, or Keras. So let's assume we have our historical training data, and for each of the sample in the training data, we know if that sample fell into a regret node. So we have this regrette list of Booleans that indicates whether the sample fell into a regrette node. And then on top, we have a regrette factor that is a tunable, or probably should be tuned, hyperparameter that now determines how much do we want to increase the loss for a sample that fell into a regrette node. Let's assume we have our training data, X-train and Y-train, and now we create a regrette weight array that we populate with ones, and then override this array with the regrette factor for all the samples that fell into the regrette node. And this regrette array we can just simply pass to a training. For example, at XGBoost, we have now set up our XGBoost classifier, and we can just pass this sample weight to the model. Similar when you use Keras in TensorFlow. Let's assume we have a model compiled. And if you're training with the NumPy data, you can also just pass these sample weights to the model, or to the training. Lastly, last example, PyTorch. We also have a nice option to introduce this here that looks a bit different. Let's assume we have set up a loss function, in this case, cross-entropy loss. And there's a nice trick just to set the reduction parameter of that loss function to none. That means this loss function will now return the sample-wise loss instead of the aggregated loss. That means when we now train our model, so we iterate over the training batches, we now have to make sure that our training data also includes a regrette weight tensor for that specific batch. And we can now do a forward prediction and calculate a loss. This is now, remember, this is now the sample-wise loss. And the sample-wise loss we can now multiply with the regrette weight. And lastly, we average this loss before we backpropagate it. So also a very nice, simple solution how we can introduce the regrette into our model training. So now that I showed you or talked about the general idea and how we can quantify regrets in such a game tree, I want to talk about a real-world use case. So I'm currently, as I said in the beginning, a machine learning scientist at Adyen, and I work on a product called Revenue Accelerate. So this is a complex machine learning product that holds several expert decision components with the goal to optimize payment traffic, for example, by doing smart messaging, smart routing, optimizing authentication, checkout optimization, and also payment recovery. And it's also a complex system where we have interactions with shoppers, issuers, card schemes, and so on. And some time ago, I was working on a model, so I was A/B testing a new model variant. And I saw that this new model variant was actually outperforming locally. So at the time point it was called, this new model was showing quite the high uplift in conversion rates. But then I also looked at the performance after all the other components in Revenue Accelerate were actually called. And what I saw is that this model that was outperforming locally suddenly showed a light underperformance globally. So what did I do? Essentially what I described in this talk today. So I kind of like reviewed or viewed this complex system that we had at hand as a game theoretical process, as a game. And that allowed me to identify some regret conditions, and I simply introduced that regret into the loss function of the model. So what were the results? So I saw, when this is the results I had before, I saw that as soon as I introduced the regret into the model, that the model started outperforming on a global level as well. And again, I showed it in the practical example. There's this regret factor, and I also tuned that factor to find the perfect sweet spot, and I ended up with something like that, a model that is now not only outperforming locally at the time point it was called, but also after all the other components in the system were called as well. So I think what I like most about this result is that this was a very small change, right? So I did not do any feature engineering, additional data. I did not increase the model complexity. But just by this very simple change, introducing the regret information into the model, was now able to successfully convert around 300,000 transactions more per month, which ended up to be around 20 million euros more for our merchants. So small change, but really nice effect. So lastly, my conclusion. If you're now thinking, oh, well, this example use case in the system that looks nothing like the system I'm currently working on, I'm sure it doesn't, because we can also imagine that machine learning systems and also these game trees that I visualized are very diverse and complex. So is this a one-size-fits-all solution? Probably not. But if you're currently working on a complex machine learning system or a model within a system, I'm asking you to maybe zoom out a bit and ask yourself, are these components all perfectly synced? Or might there be some performance loss that you're not even aware of? For me personally, describing such a system as a complex game and finding also a game theoretical taxonomy for it helped me to identify suboptimal conditions within the system. And of course, regret is only one possible solution, one instrument that we can use to optimize a complex system. Maybe that's useful for you. I think there are also other game theoretical concepts that might be interesting when we talk about these complex systems, something like common knowledge, risk aversion, dominant strategies. Yeah. With that, I'm at the end of my talk. Thank you for your attention, and I'm also happy to answer some questions if there are any.
Thank you, Laura, for the nice talk. So we have time for a couple of questions.
Hello. Yeah. Thank you very much. I have two questions. One is, I think the regret parameter that you tuned is very important in this process.
Yeah.
And I can think that depending on the problem that you're trying to solve, it will have quite different parameters. For example, if I'm trying to solve a complex problem with medical compared to finance, there should be different ways of optimizing it. So what's your best practices in that? And assuming that that's a business-specific parameter, how would you know that in your online experiment, that parameter still is a valid selection?
Yeah. So indeed, I would agree that tuning the parameter is essential. I think also in the exemplary results that I showed here, you can see that if you set this parameter wrong, you get some suboptimal decisions. I also actually saw if you set this too high, you end up with underperformance in both areas, locally and globally. So it's essential to tune this parameter. I think what makes most sense is dependent on the use case and the form of regret that you introduce. In this case, I'm talking about the model that is updated frequently on a weekly basis. So depending on the stability of the parameter that you see, so maybe you see that this regret parameter changes quite often, that it would make sense to also introduce this into the iteration of tuning, however often you tune the model. Yeah.
Okay, thank you.
Hello, thank you for the presentation. I would like to ask, how would you approach to the problem if the target is not binary but the continuous, like the generating the revenue maximization? Is it possible to define the regret? Is it with a regret factor, or would you like to approach in a different way?
Yeah, so I think the approach that I discussed today here is, of course, like a binary or multiple categorical decision tree. I think it's probably possible to also use this method in a tree where the splits are based on continuous data. To be honest, I would need to think about how to implement that, but I'm sure it's applicable to different types of problems and it's not restricted to classification per se.
Will the tuning process will be different?
Sorry?
Will the tuning process will be different for the factor?
Sorry, can you repeat the question? The
Will
tuning process.
the tuning process be different for the refactoring for the regret parameter? You said that the regret parameter can be tuned. Will the process will be different tuning the regret parameter in that case?
Well, I mean, how you tune the parameter, I think, is up to you. I think you would need to write some sort of wrapper around your model training or integrate this in your tuning process in a certain way. Of course, this can also be manually tuned, depending on how big the effect is. You just compare some models with different regret parameters. But if you want to efficiently tune this, you would probably need to write something to integrate this in your training pipeline. Yes.
Thank you.
Hello, thank you for the talk. It was very interesting. I don't think there's enough game theory in ML. I wanted to talk about the implementation, specifically when you were using the weights to kind of represent the regret. It seems like you need to have the model fully trained to understand the outcome, the regrets basically, to feed back into the weights. So how do you avoid having a cyclic issue where the weights are fixing one problem but ignoring a previous iteration's problem? So you end up kind of in a cycle where you're oscillating between different subspaces of the decision.
Yeah, so I think, of course, in a complex system where you have like changing components that might also be updated frequently, whenever you do, for example, a global optimization, so we could also try to solve this like from a global optimization problem method, right? We could, instead of train the model locally, train the model on a global level. And then we still have the issue that we're now trying to approximate these probabilistic decision models that are changing maybe over time because they're updated. And to a certain degree, this regret quantification also suffers from the same problem, right? But it also has some benefits because it can be quite stable compared to a global optimization. In this case, for example, the regret is based on a deterministic decision rule, so something that is probably not adapted quite frequent, right? So the regret should stay quite stable. Of course, when we identify regret down the tree based on these components that are frequently updated, regret also suffers from this issue and needs to be updated frequently. But some of these regret conditions can actually be quite stable, depending on where in the tree they are.
And thank you.
I think we have time for one or two more questions. Oh, yeah.
I like your approach of counterfactually weighting the loss with the regret. I was surprised to see that the regret, I think you call it the factor, is constant or global across the optimization. Have you thought about making it like dynamic or adaptive, given like the per sample?
Yeah.
Like in some cases, the regret might be larger than in other cases. So
yeah, I mean, in this specific case here, because like I'm only introducing one type of regret, right? That's at the same level of the decision tree. I think it's fair to increase the regret weight in the same way for all the samples that end up here. But indeed, I was also experimenting with integrating different forms of regret. For maybe another form of regret, additional regret node more down the line. And then I think it makes sense to also think about how do I want to weight these different forms of regret within my regret function. Yeah, so it's definitely something that might be useful that I also try to look into. In this specific example, though, I think it's fair to use a constant value because the regret nodes are all on one level, essentially the same.
Thank you.
Okay, so since there's no more questions, then join me for a round of applause for Nora. Thank you for the talk.